I'm fortunate. I have the privilege to introduce our next speaker. So it's my distinct pleasure and privilege to be able to introduce Professor Mark Dean of Columbia University. Professor Dean has published widely in the top journals in economics, including the JPE, the Review of Economic Studies, the AER, and the QJE. He has been at the forefront of using formal economic theory to model neuroeconomic data, considering the nature of decision error in economic decision making, and more recently, his focus has been on rational inattention. His topic today is rational choice overload, as we can see here. With that, I'd like to welcome Mark to the ESA World Meetings and give him the floor.
Hello, can everyone hear me okay? Wonderful. Okay, well, first of all, thank you very much for that very kind introduction. Thank you very much to Ian for inviting me, and thank you very much to the local organizers for providing me with the biggest physical stage that I've ever had the opportunity to speak from. So I'm going to make full use of that. So the paper I'm going to present today is called Rational Choice Overload, and this is joint work with a PhD student called Lucas Delara, who is on the market this year and is lovely. You should have a look at him. A couple of points that I'd like to make before I start. So first of all, you'll notice that the word rational is hanging around in this title. And basically what I'm going to try and convince you of is that the phenomenon of choice overload can in principle, and in fact in practice, can be thought of as coming about as a rational response to noise and consideration costs and things like that. And as such, I see this project as sort of a small droplet in a relatively large wave that I think is coming at the moment, which is, I think, reimagining a whole lot of behavioral economics through a sort of a cognitive lens, and think about things that maybe previously we've thought about as resulting from preferences, as really as coming about from the rational response to cognitive constraints. And I think we're lucky enough to have a panel by Ryan, Ian, and Rafa tomorrow, which is going to talk a lot more about that. And I think this is a very exciting direction in which we're going, and so I strongly recommend that panel. Friday, sorry. See? Cognitive noise. So the other part of this is choice overload. So I've been thinking about choice overload for a long time now. In fact, my job market paper was on choice overload back in 2009. That's never been published, so hopefully this stuff is a bit better than that. We'll see. Maybe I've learned something in the last 15 years. Okay, so rational choice overload. So what do we know about choice overload? Well, the one thing that we all know about choice overload is it is basically a fear of large quantities of jam. So if I give you a small number of pots of jam to choose from, you're going to say, oh, thank you very much, I really like this one on the top left, and I'll buy it. Whereas if I give you a large fraction of jams to choose from, then you panic and run out of the store and you don't buy anything. So that's the story that we know it ever since Iyengar and Lepper published their paper on this a while back. So can we say anything more about it than that? Well, yes, people have thought a lot more about it over the intervening years. So one quote from a recent meta-study is that choice overload is the paradoxical finding that providing individuals with more options can be detrimental to their choice. Well, and this is something that's been heavily studied in psychology and marketing. There are lots of papers there. And I would argue relatively lightly studied in economics, though there are, of course, some very interesting papers there. Of course, the word detrimental is doing a lot of work here, and it's been measured or interpreted in a number of ways. Some of these, I'm going to say, are sort of outside the scope of traditional economic theory, things like ex post, satisfaction, and confidence. These are not traditional objects that we theorize about, though they are things that we're starting to theorize about. However, others are sort of right in our wheelhouse as choice theorists, and in particular, there's this notion of active choice. So going back to Iyengar and Lepper, what did they show? They did two treatments in a local supermarket, one in which they had 6 jams arrayed in a display, another in which there were 24 jams arrayed in a display, with the 6 jams being a subset of the 24. And the shocking finding that motivated a lot of people, including me, is that it seems that many more people were prepared to buy jam from the limited choice treatment than from the extensive choice treatment. So there's 2% of people bought a jam if you gave them all these 24 jams to choose from, and 12% people chose when there were only 6 jams to choose from, which seems paradoxical and weird. And, of course, we can think of this as being a violation of sort of classic axioms of utility maximization. So if we think of the limited choice set as consisting of 6 jams and then a default alternative, which is to buy no jam and walk out the store, and then the extensive choice set to consist of the same 6 jams and then 18 other jams plus the opportunity to walk out the store, what this means is that for at least some people, it must be that they're choosing the option D to walk out of the store from the large choice set and not from the small choice set. And this means that we've got a violation of independence of irrelevant alternatives. So my first claim is that I think choice overload is a really interesting phenomenon for economists, if it's true. So if this result is robust, it's really interesting. Why? Well, positively, clearly, from a positive point of view, what I've just shown you is it's clearly a violation of utility maximization. So we need other models. It's also kind of hard to explain with the obvious behavioral models you might want to use. So for example, we might say, oh, well, there's a default here. Maybe this is a model of reference dependence. Well, most models of reference dependence say that if you don't change the status quo, if you don't change the default option, then people just look like utility maximizers. All the violations of utility maximization come about when you move the default around. And what we have here is a violation of IIA when you have a fixed default. So they're not going to work, so we need to think of something else. Other people say, well, look, maybe it's just informational constraints. And that seems like a promising way to go, and in fact, in a way, that's the direction I am going to go. But those models have to explain why it is that you can't just, if you're worried or stressed out by thinking about 24 options, why don't you just think about 6 options? Just randomly pick 6 from the 24 and think about those. That should work well enough. So what that means is that the explanations we have typically relied on something more exotic. So for example, the idea of contextual inference, which was Amir Kamenika's job market paper around the same time as mine. His is published. Or decision avoidance. So this is an idea of psychology. I'll talk a little bit more about these ideas later on. The other thing is that I think, again, if we think that this is a robust phenomena, then it sets up a really interesting set of normative questions. And in particular, how should we design choice sets? So if we take just the standard model of utility maximization, then giving people more alternatives to choose from can only be a good thing. Either I'm adding alternatives which are better for you than the ones that are already there, in which case you can choose them and you're happy, or they're not better than the ones already there, but that's fine, you just ignore them and you choose the best thing. But if we have choice overload, if we have this effect by which if I ply you with too many choices, then you for whatever reason, you don't make good choices, then that calls this logic into question. And we could have potentially really interesting sort of discussions about what optimal choice set design looks like when you have, say, for example, both choice overload and heterogeneous and unobservable preferences. And just as an aside, this is a sort of phenomenon that arguably has already been shown to affect many important markets that we might be interested in. So there's a recent paper by Olivier Nathan showing overload in product markets. There's an old paper by Iyengar and Kamenika showing it in 401k, another paper showing it in health insurance markets. Having said that, I think that the first question, before I sort of devote the rest of my life to trying to understand choice overload, is whether it in fact is a phenomenon that exists and can be robustly shown. And following on from the Iyengar and Lepper study, the picture has been a lot more mixed. So there have been some direct replications that have failed. There have been some meta-analyses that have found a mean effect of 0. So if you average over all these things, then you find an average choice overload effect of 0. And then there are others, like this Chernev study that I talked about before, which does suggest that there is a choice overload, but only in particular situations. So it's rather specific when this turns up. So this leads to a sort of research agenda that I've been working on for a little while. The first is to try and ask the question, does choice overload really exist? And I have a paper with Jorg Stoy and Dilip Ravindran, which I believe sort of quite comprehensively gives the answer yes. And basically what it says is that existing tests of choice overload have been very low powered, and this means that we must be finding less choice overload than there typically is, and it explains why we have sort of inconsistent findings and stuff like that. The second paper is the one that I want to talk about today, where the next question is, of course, what's causing this choice overload? And here I want to focus on the role of search and rational responses to information costs. So that's the paper that I'm going to talk about today. And then, of course, the final question, the pièce de resistance here, is what should we do about it? And at the moment, I have no idea, because I've been busy answering the first two questions. But I think that answering these first two questions is a necessary first step into answering these third questions. It's hard to know how we should design choice sets in the face of choice overload if we don't know the mechanisms that are driving choice overload in the first place. Okay, so my dream scenario was to talk you through quickly the first paper and then move on to this rational choice overload paper. I think given the fact that we started late and it was always a bit of an ambitious agenda, I'm afraid I'm going to switch straight to this second paper on rational choice overload. The first paper is also fascinating, and I'd be more than happy to talk to anyone about it if we afterwards or through the course of the Congress. Okay. So, hopefully I've convinced you that choice overload is a thing. Hopefully you trust me that choice overload is a thing. And now, what I want to do is talk about what causes it. We also would have had some clues. And these clues are, first of all, you don't get choice overload from every small set. So when you go from any small set to any big set, you don't find choice overload all the time. And in fact, when it does happen is fairly predictable. It happens when you increase the size of the choice set by adding in options that are bad relative to what was already there. So if I take a choice set and I fill it with a bunch of crap, then that's when I'm going to get choice overload. And then the finding from the Chernev paper, which is not mine but I already referred to, is that we seem to get choice overload when options are unfamiliar and difficult to understand. So putting all this together, I think that this at least hints at a possible explanation in which what happens is that subjects, when faced with a large choice set, they take a look at it, but if they don't quickly find something that they like or something that's better than their default alternative, then they're going to stop and they're going to back out and not make an active choice. So that's the sort of intuition that I want to look at in this paper. And so what I'm going to do is present a model of sequential search that's going to give rise to choice overload. And in doing so, I'm going to try and answer three questions. First, can a model of optimal sequential search give rise to choice overload? Second, what are the features of the search problem that lead it to occur? So what has to be true about the setup of the search problem in order for us to get choice overload? And then three, if we run an experiment, is this search channel that can generate choice overload one that's empirically important? So those are the three questions we're going to try and address today. And the way I'm going to do it is I'm first of all going to introduce the data that I'm going to use and the representation of that data that's going to be our sort of workhorse. I'm then going to start talking about optimal models of sequential search, and I'm going to show that the first result is going to be that a standard model of sequential search, perhaps the first one that you think about, in fact, can never give rise to choice overload. It just won't do it. However, I'm then going to try and persuade you that this is a fairly knife-edge case, and there are three modifications to this model which pretty immediately do give you choice overload. I'm then going to talk us through an experiment that's going to allow us to differentiate between these different variants, these different search models, and also these different search models on the one hand, and sort of classic explanations for choice overload, like contextual inference, like decision avoidance on the other. So that's the aim that I have. Okay, so let's start with the setup. So, as before, or seeing it for the first time, I'm going to think about a case in which there's a universe of X possible alternatives out there. Let's think about this as all the possible jams that you could be asked to choose from. And then there's going to be a default D, which you can think of as walking out of the shop without buying a jam. I'm actually going to think about two types of data here. The first type of data to make standard economists happy, and then the second type of data to keep Ian happy, because that's going to be the process data. So the first is just going to be standard stochastic choice data. So here, what we're going to assume is that for any given choice set, big A, I observe the probability little a, the probability that you choose little a from that set. So P little a big A is the probability that you choose little a from set big A. By the way, sorry, again, this is slightly out of order because I've skipped a little bit of stuff. But we're going to assume that the big set A always contains the default. So you always have the option of walking out of the shop if that's what you want to do. And the reason that I'm going to want this data set is that this data set is the one that I'm going to use to determine whether a particular model can give rise to choice overload. And the reason I can do that is I'm going to define choice overload as an increase in the probability of choosing the default as I move from a subset to a superset. So I increase the size of the choice set, I add things to the choice set, and somehow that makes you switch to picking the default. So this is just the definition that Iyengar and Lepper used. I'm then going to also think about an experimental choice data set, and I'm calling this experimental because it's the type of data that we're going to collect in our experiment. And this is going to allow us to look a little bit more under the hood about what type of behavior it is that is underlying people's choices. So this is again going to be a probability distribution, but in this case it's going to have three arguments, X, Y, and L. So L is going to be the choice list. So now in this case I'm going to think about people as being presented not just with a set of alternatives to choose from, but an ordered set of alternatives to choose from. So in other words, I'm going to assume that I can observe the order in which they search through alternatives. So that's going to be L. I'm then going to observe the probability that search stops at a particular point in L and that a particular alternative is chosen. So I'm going to observe that joint distribution. So rho X, Y, L is the probability that I move along list L, and I stop at point Y, and I choose option X. So it's the probability that I stop at Y and choose option X when faced with a list L. As I mentioned, I'm going to classify this as process data because it's going to give us some insight into the choice process that people make. And the reason it's going to be useful for us is it's going to allow us to differentiate between these causes of choice overload. Let me put it slightly differently. It's going to make it much easier for us to differentiate between these different causes of choice overload. And as I said, this is the type of data we're going to collect from the experiment when we get there. Okay, so that's the data. The next thing I want to do is introduce a generic model of sequential search. So at the moment, there's nothing optimal happening. I'm just going to introduce a model, a sort of just a general all-purpose model of sequential search so we can understand how sequential search relates to our data. And then, once I've done that, I'll then think about introducing models of optimal search which are going to put constraints on this generic model and allow us to make predictions. So at its basic level, I'm going to think of a model of sequential search as one that consists of two objects. One is a utility function U, which says how much these alternatives are actually liked. So this tells us how much we like each of these jams. And then it's going to have a distribution over threshold functions. So what's a threshold function? I'm going to use this little tau as a threshold function. And what you plug into tau is L, which is the sequence of utilities that you've seen so far. and then you're also going to plug in an n, and this n is how many alternatives there are left to search. So, and what it's going to spit out is a utility threshold that's going to determine whether or not you stop searching. So that's what a threshold function is. The reason I'm going to talk about distributions over threshold functions is that without this distribution, everything in this model will be deterministic, and I want to be able to match stochastic choice. So I need some stochasticity to come from somewhere, and I'm going to have this stochasticity coming from the fact that different people may have different threshold functions. So this may sound a little bit mysterious at this level of abstraction. I don't think it is mysterious, so let me just give you a concrete example. So let's think about someone who's faced from a choice of list L. So L consists of D, X1, so D is the default, that's always the first thing you search, and then X1, X2, all the way up to X minus 1. So how does this model imply that you're going to make a decision? Well, the first thing you're going to do is you're going to put your hand in your bag of threshold functions, and you're going to draw one out. So this is now your threshold function. You're then going to look at the first element, D, and you're going to say, okay, now I've looked at D, I know what the utility of D is. That's UD, okay? So good, I know that the default gives me a utility of 6. Now, am I going to bother to continue searching? Am I going to look at the next alternative in this list? Well, in order to determine that, what I'm going to do is I'm going to compare this utility of D to the threshold I get when I plug in the list of alternatives I've seen so far, which so far I've only seen D, and the number of alternatives that I have left to search, which in this case there's n minus 1. So I say, okay, at the moment, the utility, I've seen a utility of 5, I have 12 items left to search, okay, that tells me what my utility threshold is. And then what I'm going to do is I'm going to compare that utility threshold to the best utility I've seen so far, which in this case is just the utility of D. If the utility of D is above that threshold, then I'm going to say, okay, great, I've achieved my goal, I'm above my threshold, so I'm going to stop searching and I'm just going to choose the best thing I've seen so far, which is D. If not, if the threshold is above the best utility I've seen so far, then I'm going to continue searching. So in this case, that means that now I'd look at the next alternative, UX1, and I'd say, okay, so now let me look to see what's the best utility I've seen so far, which is going to be the max of UD and UX1, and compare it to my new threshold. What's my new threshold? Well, it's the threshold my threshold function gives me when the things that I've seen so far are D and X1, and there are n minus 2 alternatives left to search. So now I'll compare the best utility I have so far to the threshold. If the best utility I have is above the threshold, I'm going to stop searching and choose the best thing I've seen so far. If not, I'm going to carry on, and so on and so forth. So this is a model that sort of generates a process of sequential search. Yeah, so I'm going to, so one of the things that I've punted on at the moment is what's the defining characteristic of D. But what I want you to think about it really, the basis of this model is that D is going to be sort of your outside option and something that you already know the value of. So maybe you even come into the decision problem knowing this value. So think of the jams. I already know what the value I will get if I walk out of the shop is. What I don't know is what the utility of these jams are. So yeah, I'm going to assume that D is something that you sort of get to know for free. So if you give me one of these sequential search models, this generates an experimental data set. So it gives me predictions about the joint distribution of stopping and choosing for any choice list. This experimental data set generates a standard data set row, which tells us the probability of choosing each of these alternatives in each of these choice sets. And sorry, one of the things it doesn't say here is that then we can look at those standard that standard choice data set and understand whether this search model will allow us to get choice overload. So what we're going to do now is use this machinery to understand the behavior implied by different optimal models of search. So optimality is going to restrict the support of these threshold functions. So different concepts of rationality are going to tell us which type of threshold functions we can be looking at. That in turn is going to tell us what characteristics our experimental choice data set can show, and in turn that's going to tell us whether or not we can give rise to choice overload. So that's the setup. Yes? Okay, right. So yes, in the experiment, in the experimental data set, yeah, the sequence is given to you in the same way that a choice set is given to you. What we are implicitly assuming when we go from the experimental data set to the standard choice data set is that these alternatives are ex ante identical. So you can't direct your search. You can't say, oh, I have some sort of like weak signal that that option, that jam over there looks good, so I'm going to move towards that. So what we assume is that basically there's an exogenous distribution over search orders. So one could think about extending this to a case in which, you know, maybe these alternatives appear on a search page, and so I get some free signal based on the order they appear on the search page. My belief is that that would add complexity to the model without really affecting the main lessons which I'm going to provide here. Yeah, I think that's true, with one possible exception. Okay, so now we've got this set up on the table. Now I can talk about specific models of optimal search, and we can think about whether or not they give rise to choice overload and how we could spot whether this is what's going on in the search data. So I'm going to think of it like first of all, I'm going to think about what I consider to be sort of the simplest sequential search model you can think of. The decision maker is faced with a set of alternatives. Initially, they only know the utility of alternative D, the default. But they can search through these alternatives one by one. But every time they look at a new alternative, they have to pay some fixed cost K to look at it. Once they've looked at that alternative, and that reveals the true value. And so at any point, they can decide, the decision maker can say, right, I'm either going to stop searching and pick something, or I'm going to have a look, I'm going to pay another cost K and look at another alternative. So formally, the decision maker is faced with a list of length n, which is drawn from some set x. They are equipped with a utility function, so once they identify what each of these alternatives are, they know their value. Importantly, they have a probability distribution which reflects how good they think this choice set is, in the sense that this tells them that when they look at a new alternative, what this F says is this is their beliefs about the distribution of values that they're going to be drawing from. So how likely it is that they're going to get something good and something bad. And then they have a per object search cost K. So every time they search something, they pay a cost K. And then at any point, the decision maker has two options. They can either stop searching and choose the best alternative seen so far, or they can search another alternative, in which case they get to draw something from this distribution F, and they pay a search cost K. And what they're going to do is they're going to choose a strategy to maximize the expected utility of the thing that they're going to walk out the shop with, net of these search costs. So that's what we mean by optimality. So, first question. Can this model explain choice overload? Well, as I've sort of hinted quite strongly by saying it, the answer is no. Why is that? Well, what we showed in our 2011 paper, and we were very proud of until we realized that this was a very special case of what Weissman showed in his 1979 paper, is that the optimal strategy in this environment is a fixed number. That there is just a fixed reservation number, and that number is independent of the size of the choice set or how many alternatives you have left to search. Excuse me. So that means that we don't know what that number is, because it's going to depend on the beliefs of the subject and it's going to depend on their costs, but we know that they should have this fixed number. So why can this mean that we can't get choice overload? Well, let's say from some small set A, we know that A wasn't chosen. Sorry, we know that the default wasn't chosen. Some other alternative was chosen. What does that tell us? Well, first of all, If the default wasn't chosen, that means that search must have started, that people must have started looking at other alternatives. If they didn't look at any other alternatives, the only thing they could do is choose the default. So we know that this person started looking at other alternatives. But if they started looking at other alternatives, that must mean that the utility of the default is below their threshold. Okay? So that's one thing that we know. And the second thing we know is that there must be something in this choice set that is better than the default. Okay? Because they didn't pick the default. So whatever it is that they chose must have had a utility higher than the default. Either that it's also higher than their threshold, or they just searched through everything and they stopped searching, but they found this alternative that was better than the default. But both of these things still have to be true in any superset of A. So if B is a superset of A, and we now set our person going to choose from B, well, first of all, we know that they're going to start searching, because we know that the utility of the default, which is the first thing they look at, is below the utility of the threshold. So that means that they must start searching. And we also know that given that B is a superset of A, there still has to be something better than the default in there, because there's something better than the default in A, there has to be something better than the default in B. So that means that this person is going to keep searching until they find this at least find this better alternative. Maybe they'll find another better alternative, but they're going to come across something that's better than the default. So that means that there's no way that they can choose the default. Okay, so this seems to be a bit of a problem for our project, which is to explain choice overload using models of sequential search. But what I'm going to claim is that this standard model is really a knife-edge case. And you only have to change things a little bit before you get a search model that certainly is going to give you choice overload in the right circumstances. And in the paper, we talked through 3 different alternatives, which I've listed here in, I think, decreasing order of interest. So the first one is fairly interesting. The last one is not very interesting, but they're all possibilities. The first is the idea that maybe you're learning about the quality of your choice set as you go along. And the second is that the possibility that due to fatigue or something like that, you have increasing search costs over time. And the third is that rather than doing dynamic optimization, where you dynamically compare utility alternatives to the threshold, instead maybe you do static optimization, where you just you decide at the start how many alternatives you're going to look at. So let me first talk about learning. I'm sorry, I've literally no idea how long I've been talking about it for. Does
31 minutes and 5 seconds.
Okay, I now have a very precise idea about how long I've been talking for. Okay, good. I think we're on course. So let's first of all talk about learning. So what is it that the standard model is missing? So I'm convinced that the fact that search can be used to explain this idea of choice overload, but I've got this standard search model and it's not doing the job, so what could it be missing? Well, I think the first thing, and to me, both the most obvious thing it's missing and I think also the most interesting thing it could be missing, is that maybe people don't know how good a choice set is, and they have to learn about it as they go along. So, imagine that you go into a jam shop, and you pick up the first jam, and you're like, ooh, shrimp jam, that sounds disgusting. Bark jam? Liver jam? Where am I? What is going on here? One assumption you might make here is that you are not in a very good jam shop. You're in a jam shop that sells terrible jam. And a sensible thing that you might do at that stage is say, well, given that this is a terrible jam shop, I'm going to leave and I'm going to look for jam elsewhere. And what that might mean is that you would fail to find the delicious strawberry jam that was in there, but your beliefs about the quality of the jam shop were such that, you've just given up on this jam shop and you've gone elsewhere. So how can we incorporate this into our model? Well, what we're going to do is we're just going to make one little change. We're going to say that rather than there being just this one fixed distribution F, which is the quality, I believe this to be the quality of alternatives I'm drawing for, and it's immutable, and I will never change my belief regardless of what the evidence is. Instead, I'm going to assume, to make things very simple, I'm going to assume that the decision maker thinks that there are 2 possible distributions they could be drawing from. They're either in a good jam shop or they're in a bad jam shop. If they're in a good jam shop, they're drawing from distribution F1. If they're in a bad jam shop, they're drawing from distribution F2. And in order to make these good and bad, let's assume that F1 first order stochastically dominates F2. Actually, sorry, it doesn't say it on here, but we're also going to want the monotone likelihood ratio property. So in this case, it means that the state of the system, so let's think about this learning system. So I'm trundling along, and I have to decide whether or not to carry on searching. Well, what would I base this decision on? Well, it turns out that in this case, there are three things that I need in order to make my decision. One is y, which is the highest value thing that I've seen so far. So we had that last time. The other is mu, which is my current belief about how likely I am to be in the good jam shop. So in particular, mu is my belief about the likelihood that I'm drawing from F1. And then 3, it is now also important for me to know the number of alternatives that there are left to search. And what I'm going to show you with a simple example is that this model can now generate choice overload. So let's think of a really simple example, one in which there are, sorry, is there a question back there? That's right. I think there are other ways of learning that are not just experiential, right? I've never tasted shrimp jam, but I'm sure it's terrible. So I think that, but yes, you're right. That if you just looked at these things and were like, and they were just labels to you, it's like X, Y, Z, then that's not going to give you anything. But if you're in that world, then none of this makes sense, right? Because this is a case in which when you pay the cost K, what you're learning is the utility of that alternative. So that was also true. We need that even for the simple model. That's kind of inherent in here. One could think of other models. One could certainly complicate this model by thinking about cases in which, I learned something from the label, but then maybe I learn more by taking it home and eating it, so I have this two-stage learning process. And there are actually models of choice overload that differentiate between experiential utility and sort of predicted utility. So there are others that take this route. I think for the particular story I want to tell, that's adding sound and fury without sort of further understanding. Any other questions? Good. Okay, so we're going to think of a case in which there are 3 alternatives. There's the default, and then there's X1 and X2, 2 different jams. And I'm going to assume that the utility of the default is below the utility of X2. So if you ever come across X2, then you're certainly not going to choose the default. You're going to choose that instead. And then I'm going to assume that there's some prior mu naught, which is your initial likelihood that you're drawing from F1. So first of all, remember I want to show that this is going to give rise to choice overload. So what I need to do is I need to show a case in which the default is not chosen from the small set, but is chosen from the larger set. So here's how we can construct that. So first of all, let's imagine that, let's think about the small set, which consists of the default and X2, which is, remember, the one that we know is better than the default. So what's the decision maker going to do? Well, they're going to start searching if, in this case, sorry, there's a U missing here, but if the utility of the default is below some threshold R, and this threshold R we can think about as being implicitly defined by this equation. And this equation is just, here's the cost of searching, and this is the benefit of searching, understanding that there's only one alternative left to search, and that my beliefs are governed by this mu naught. So let's assume that that's the case. So that means that the decision maker is going to say, okay, the utility of the default is below my threshold. I need to do some searching. I'm going to look at this next thing. Oh, what do you know? It's got a utility. This X2 is lovely. This is a really nice jam. It's better than the default. I'm going to choose that. So that means if we parameterize the problem in this way, the decision maker is not going to choose the default in this choice set. Now let's think about what happens from the set D, x1, x2. And let's assume that the decision maker is just exogenously going to search through in this order. They're going to search D first, then x1, and then x2. It's very easy to show that if the decision maker was prepared to start searching in the first choice set, in the small choice set, they're also going to be prepared to start searching in this bigger choice set. And the reason for that is that the threshold is increasing in the number of items left to search. So here there are more items left to search, so they're going to be more willing to start searching. So that means that, and let's assume that the first alternative seen is x1. What's going to happen then? Well, the decision of whether or not to continue search is going to depend on two things. First of all, their updated beliefs about the probability of f1. So now they're going to look at this, they look at x1 and they say, oh, x1 has a utility of 6. That's going to update two things. It's first of all going to tell them, it's going to change their beliefs about the relative likelihood of f1. So it's going to change their beliefs about whether they're in a good jam shop or a bad jam shop. And it's going to change the highest value thing that they've seen so far. So it's going to change the max of these two things. And so the optimal strategy is going to look something like this. So on this axis, we have beliefs. Going from here, I think it's certain to be the bad jam shop. Here, I think it's certain to be the good jam shop. And here's the value of the best thing that I've seen so far. And what the optimal strategy looks like is there is a sort of an upward sloping line in this space. So up here, I stop searching, and down here, I continue to search. So what this means is that if I fix beliefs, then as I increase the value of the best thing I've seen so far, then if there's a low value, then I'm going to carry on searching. If there's a high value, I'm going to stop. That's very standard. But also, if I fix a value of the best thing I've seen so far, if I have very low beliefs, then I'm going to stop searching, because this says, oh, very likely I'm in a bad jam shop, so I'm not going to find anything that's good. And as these beliefs go up, then at some point I'm going to say, oh, actually, you know what? I'm fairly convinced that this is somewhere very nice, so I'm going to carry on searching because I think it's more likely that I'm going to find something good. So where I am in this space is going to depend on the utility of this x1 that I draw. And this is going to, and so for x1, if the utility of x1 is below the utility of default, then that means that as I increase the value of x1, then this increases my beliefs, but it doesn't increase the value of the best thing that I've seen so far, because that's still the default. Whereas if ux1 is higher than the utility of the default, then if I increase ux1 further, then I increase both my beliefs and the value of the best thing I've seen so far. So what that means is the locus of possible points that I could get looks like this. And what this is going to do is it's going to give us three regions. Up here, if the value of x1 is really high, then I'm going to stop searching. And this is just the classic sort of sequential search logic. I found something really good. That means that the probability I'm going to find something even better is pretty low, so I'm just going to stop and choose this thing. In this middle region here, then for intermediate values of x1, then I'm just going to carry on searching. It's like, well, the thing I've seen isn't very good, but my beliefs are high enough that it's worth for me to carry on searching. The interesting region, and the region that's going to give us choice overload, is this fella down here. So if I now see a jam that is truly terrible, I'm also going to stop searching. And the reason I'm going to stop searching is this has now pushed my beliefs down so far that despite the fact I think x1 is terrible, I'm still better off sticking with the default, because I now think the chances that I'm going to find something good in this choice set are just too low. So the benefit of search has just been pushed right down, and I'm just going to stop searching. So that just summarizes what I've just told you. So what that shows us is that a model which includes learning can give rise to choice overload, but it gives a rather specific pattern. So, if we have learning, it can give us choice overload, but it's only going to give us choice overload if in the big choice set the decision maker starts searching, but then gives up before they find something better than the default. That's the only way it can give us choice overload. Moreover, this model is going to predict that the probability of choosing the default is going to increase the further back good alternatives appear in the list. So if I think about the position of the first above default alternative, the further back I move it, if it appears in position 1, then I'm very likely to find that and I'm just going to choose it. If it appears in position 20, so I have to slog through all this rubbish in order to get there, I'm very likely that my beliefs are going to get depressed and I'm going to stop and I'm going to choose something better than the default. Also, if we look at the probability of search stopping, it's going to depend on my beliefs, so how likely I think it is that I'm in the good choice set, the number of items left to search, and the value of the best alternative C. And I'm just going to put this in this table. Right, despite the limited scope of my presentation, I'm also wildly running out of time. So what I'm going to do is I'm going to talk quickly about increasing search costs. I'm going to skip the static optimization and then move swiftly towards the experiment. So I said that the other possible reason that search might give you choice overload is if you have increasing search costs. So if the more you search, the more tired you get, and that's going to give us choice overload as well. Why is that? Well, if you have a model in which the more you search, the more tired you get, and that implies that your cost of search increases, it's pretty easy to show that what you then get is you get a threshold which is decreasing over time. So initially you're very keen and you have to see something very good in order to make you stop search, but the more you search, you're like, oh God, this is really exhausting, I'm ready to give up and just choose anything. So the threshold is now a decreasing function of the number of items searched. And then it's pretty easy to see, and in fact it's fairly mechanical to see that that can also give you choice overload. So let's say that we have 3 alternatives, x1 which is worse than the default and x2 that's better than the default. And now we have a threshold that is decreasing over time. We could parameterize this model in such a way that if I've only searched one alternative, then the utility of the default is below the threshold, so I want to keep searching. Whereas if I've searched 2 alternatives, then the threshold is below the utility of the default. So in this case, if you just gave me the list D and X1, D and X2, then, first of all, X2 is the first thing. I'm prepared to move away from D because of this inequality. So I say, oh, look, I'm going to have a look at X2. Oh, yeah, no, that looks pretty good. However, if you put X1 in between D and X2, then I move from D to X1, and I say, oh, well, X1's worse than default, and also my threshold's dropped because I'm now tired. So in fact, the default now looks pretty good. It's above my threshold, so I'm just going to stop at this stage, and I'm going to choose the default. That's giving me choice overload. So we can get choice overload. It gives us a very similar pattern to what we got from the learning model, except now the thing that determines stopping is not the beliefs and the number of items remaining. It depends only on the number of items searched. Okay, I'm going to skip static optimization because it's very similar. What I do want to do before I talk about the experiment is to talk a little bit about classic models of choice overload, which are decision avoidance and contextual inference, because I'm going to want to compare to those and say we can sort of rule them out. So decision avoidance is an idea that's sort of got a long and venerable history in psychology and some in economics. And the idea is that choosing from large choice sets is aversive because in some sense it's a hard choice to make. So if you give me a large thing to choose from, then I find that an aversive and upsetting thing to do, and I look for ways to avoid engaging with that choice set. On the other hand, contextual inference is the idea that maybe I can learn something about the quality of a choice set simply by the number of items in it. And in particular, the basic mechanism is that the larger the set of alternatives, the lower, I believe, the average quality of each of those alternatives, or the worse fit I believe it's going to be for me, the lower my utility is. So how can we think about these in a search context? Well, obviously, they are going to give rise to choice overload. That's what they were designed to do, so of course they do. But they're going to give a very different pattern. And the reason being is that these models give rise to choice overload if it's the case that you just don't engage with the larger choice set. So remember, in the search models, what happens is you start searching and you just get dispirited and you stop and you go off and do something else. In these models, crucially, what happens is the reason you get choice overload is you give me a large choice set and you just say, oh, this is going to be either this is going to be a bad choice set or this is going to be very hard for me to get involved in. So I just don't engage in the choice problem in the first place. And what that means is that, first of all, search doesn't start in the larger choice set. So if I could look at your search hit pattern, then these models of choice overload would say, I give you a large choice set, and you're just like, nope, I'm not going to look at anything. And also, relatedly, it means that whether or not you choose the default doesn't depend on the position of the good alternatives. I can put the good alternatives up front, I can put them at the back, it's going to give the same thing. Yeah, I think I've given you the logic of that. So if we add this to our table, then I'm going to call these classic models of choice overload. And of course, they're still going to give us choice overload, but they're going to give us a very different pattern from these search-based models. So in the search-based models, then you get choice overload if you start searching and then you just don't find anything good enough, so you stop. In the classic models, then you get choice overload if you just don't engage in the choice set in the first place. And in the search-based models, if I push good quality alternatives later in the choice list, then that's going to make it more likely, that's going to make it more likely you choose the default. Whereas in these classic models, that's going to have a no effect. Because again, in these classic models, you're just not engaging in the choice set. Okay, so finally, the experiment. How long? 50, perfect, he says optimistically. Okay, so hopefully what I've convinced you of, this time, is that the theory shows that search can lead to choice overload. But of course, the theory shows that contextual inference and decision avoidance can also lead to choice overload. So how can we run an experiment that's going to allow us to differentiate between these different alternatives? So in particular, I want to ask two questions. First, is search an important channel for generating choice overload relative to existing explanations? And second, if it is, what are the features of the search problem? You know, I've laid out 2.5 possible features that could drive it. Which of those features are important in driving this effect? So I want to design an experiment to do this. What are the key design features that I want? Well, my life is going to be a lot easier if I, as the researcher, know the value of the underlying alternatives, because then I can talk about whether this was a good alternative or a bad alternative. So it's going to make my life easier if I know what the value is. But of course, I need there to be some cost to the subject to figuring out what the value is to them, because if not, these problems are just going to be trivial and they'll just look at everything and they'll choose the best thing and there'll be no opportunity for choice overload. I need to make search order and stopping observable, because that's how I'm going to make my experimental data set observable, which is going to be crucial for differentiating between these different models. I want a default alternative that's always available and always going to be the first one that's searched. And I also want a data generating process that is explicit. So I want to be able to control what my subjects think about where these alternatives are coming from and allows for learning. So the explicit is going to be important for me to be able to calculate sort of at least a Bayesian benchmark for what beliefs are. And allowing for learning, you know, if I make it explicit that there is no learning in this situation, then that's kind of automatically shutting off one of the channels that I'm interested in. So how are we going to do this? Well, we're going to make people choose between sums. Sorry, this was explained previously in the longer version of the talk. But what these sums are is that you get I'll show you them in a minute, but you get a sum on the screen, 4 plus 2 plus 7 plus minus 6, and the value of that alternative basically in monetary units is equal to the value of that sum. So easy for us at the experiment, assuming that more money is preferred to less, we know what the valuations are, but take some effort for the subjects to uncover what they are. In order to make search and stopping observable, the subjects are going to be presented by a set of alternatives, and then what they're going to do is they're going to have a button they can press, and by pressing that button, is going to reveal the next alternative. So we can see what it is that they've searched by, or we can at least approximate what they've searched by looking at what it is that they've uncovered. There's going to be a default alternative, which is going to be at the top and is always uncovered, so they get that for free. And so overall, what does this look like? It looks something like this. That up here is the default alternative that's uncovered. So in this case, the default is 6. And then in this case, they've already uncovered 3 alternatives. So they uncover alternatives by pressing this uncover button. So they've uncovered 3 here. They can look at those. And then when they find something they want to choose, they can click on that alternative and then press the choose button down here. So here they've clicked on this alternative, and they're going to press choose down here. So that's what the experimental interface is going to look like. In order to give the learning channel a fighting chance, they're going to be told that the values are drawn from one of 2 distributions. So this is distribution A, this is the good distribution, this is distribution B, this is the bad distribution, these are the histograms. And subjects see these 2 distributions, they're shown to them like this, and also to sort of try and maximize sort of our effect, they also experience this distribution. So we make them take a bunch of draws from these distributions so they know what they look like. So the distribution in play is determined randomly in each round for each choice set, but it is fixed for that choice set. So they're not told, of course, which distribution is used, but this is a setup in which learning can take place in the sense that they can make inferences about whether they're in the good or the bad distribution based on the values that they've seen. So that means that we can calculate the Bayesian beliefs, and we're going to use that in our analysis. And, you know, I'm happy with this. Others may see this as a cheat, but the subjects are explicitly told that, you know, hey, the likelihood of this being the good distribution can change depending on what it is that you've seen. So we ran this on Prolific because we wanted a lot of data from subjects not making very many choices each. Each subject made 10 choices. 4 from small choice sets of size set 2, 2 from choice set size 11, 2 from 16, and 2 from 21. 1 round was chosen for payment. Sorry, it's not a between subject design, but there are 307 subjects. So that's what the experiment looks like. So first question, do we find choice overload? And the answer is yes, we do, which is good. So what this is looking at, and we believe this is the right metric for looking at choice overload, this is, in each of these cases, we're looking at the sets of this size in which there was an alternative that was better than the default, okay? So there were 53 small choice sets in which there was something better than the default, 274 large choice sets in which there was something better than the default. In the small choice sets, if they're conditional on there being something better than the default was chosen only 9% of time. In the large choice sets, that goes up to 44%. So we've got a whacking great big choice overload effect here, right? It's about 33%, which is good, because we want to try and understand what's driving it. Oh, and yeah, in case, the phrase of the day seems to be for those that like regressions. So for those that like regressions, here's a regression. Everything's very significant. So question 2, how important is search versus non-search explanations for choice overload? So I'm going to look at this in 2 different ways. In the first case, the first way I'm going to cut this data is I'm going to, again, look at choice sets that contain an alternative that is better than the default. So these are the ones where, in principle, we could get choice overload. And I'm going to look at cases in which the default is, in fact, chosen. So there was something in this choice set that was better than the default, but they didn't choose it. So you can categorize this into 3 different possible categories. The first of which is that search just never starts, okay? That, you know, they're presented, here's like 21 alternatives on the screen, there's the default, they never uncover anything, they just say, right, I'm sticking with the default on away I go. I'm going to call that the classic choice overload, because that's what you get from models of contextual influence and inference and models of decision avoidance. The second is cases in which search starts. So people start looking at alternatives and they go, oh, yep, no, yep, yep. But they stop before they find the good alternative. So that I'm going to call called search. The third possibility is that they have, in fact, uncovered a good alternative, but they don't choose it, okay? So this is something that's outside our model, and I'm going to call this mistakes. So this is that you've uncovered something and better than the default, but you just never choose it. So here's a table. So here's the fraction of time in which the default is chosen. And this is what happens in each of the different sizes. And what I've done down here is I've subtracted, for each of these columns, I've subtracted the number of times this happens, whatever is going on in the column happens, in choice sets larger than size 2, minus how often it happens in size 2. And so in this first column, we're just looking at the fraction of the time the default was chosen. And so this 32% percentage point number here, this is really the amount of choice overload that we're trying to explain. So what we're then going to do is we're going to decompose it into each of these different causes: classic, search, and mistakes. So the first thing to note is that the search channel is a lot bigger than the classic channel. In fact, it's about 4 times bigger. A relatively small fraction of this choice overload is being driven by people who just don't engage with larger choice sets. A far larger fraction is being driven by the search channel. These are people, remember, these are people that have a look at the choice set. They say, oh, yeah, I'll have a look at 3, 4, 7 alternatives. I've not found anything good. I'm gonna quit. And they never find a good alternative. A second and slightly more awkward point for us is that this mistakes channel up here is quite big. And this is something that's not in our model. And frankly, it's something we're still looking into. One possibility is that this here is an upper bound on the number of mistakes we get, because one strategy that people could do is that they could just uncover a bunch of alternatives and then sort of start to look through them at their leisure. So the number of things that we count as being looked at is actually an upper bound on the number of things that has actually been looked at. So there is this mistakes channel here. We're thinking more about it. But I think the key takeaway from our point of view is that if you look at classic versus search, then search kind of knocks classic into a cocked hat. A second way we can look at this is that we can say, is it the case that the position of the first above default alternative is predictive of whether or not the default was chosen? So again, remember that the search model says that yeah, because I'm searching through these things one by one, if you position something good right at the end of the search sequence, then that's going to make it much less likely that I find it relative to if it's up front. On the other hand, in these other models where you're just not engaging in the choice set in the first place, you can put the good alternative up front, in the middle, at the back. It's not going to matter because you're not even opening the box. And unsurprisingly, we found strong order effects. So this is the probability of choosing the default, conditional on the position of the first above default alternative. And what you can see is that there's a sort of strong increasing pattern, at least in the first half here. So again, this is consistent with a search-based explanation where, you know, if you make me look through 19 terrible jams before you find the good one, then you're much less likely to find the good jam. So I'm going to say that those two results suggest that these search channels are as strong relative to sort of classic decision avoidance contextual inference channels. What that doesn't help us do is differentiate between these different search channels. And in particular, on the one hand, we've got this learning story where if you show me a bunch of bad stuff, I get dispirited and I stop searching, versus a fatigue story which says that just the more I search, the more tired I get, so I stop searching. Notice that both of these would predict that if you put good options later in the search sequence, I'm less likely to find them. So that doesn't help us differentiate between these two. So how can we? Well, what we can do is we're going to look at whether beliefs play. Remember, we can observe beliefs for a given sequence because we know what the we know what the distributions are and we know what people have observed, so we can look at beliefs. So what we can do is we can look at whether or not beliefs play a role in default choice, controlling for the position of the first above default alternative. And so here we're using the fact that we have random variation in the search sequence to give us this random variation. So that's what we do here. So what I'm showing you here is the result of a bunch of regressions. So the number here, so this is looking at all cases in which the first above default alternative appears after point 3. And then it's asking whether beliefs at point 3 are predictive of whether or not the default was chosen. So what we'd like to see here is negative coefficients, because what we'd like to say is that higher beliefs encourage you to keep searching, so that means that you're less likely to stop and pick the default. And what we see is that the effects are pretty weak early on, but as we get later, there are really strong negative effects here. So that, for example, here, if you've got to position 10 and you've still not seen a good alternative, then the higher beliefs you have at position 10, you're much, much less likely to choose the default. So if you've not seen something that's better than the default, but you've seen alternatives that look pretty good, then you're much more likely to carry on searching and pick something better than the default. The final thing I want to do is sort of show you the results of a behavioral equation, which looks at a behavioral model where what we do is we look at the probability of whether or not people have stopped searching at every given point on the search sequence. So we've got lots and lots of data. And what we want to look at is what factors determine the stopping decision. Because again, remember, this was a good way of us distinguishing between these different search models. And so what I'm showing you here, so this is the probability, the impact of whether or not search has stopped. And these are the independent variables. Minimum beliefs is the lowest belief, how bad your beliefs got in the path up until this point. Searched is the number of items that you searched, and items remaining is the number of items remaining to be searched. So remember, the fatigue model predicts that this number should be positive, whereas the learning model predicts that this number and this number should be negative. And what this shows us is that we've got very significant evidence that both of these things are going on. That beliefs play a role, but also controlling for beliefs, fatigue also plays a role. So it seems like the best model would be one that has both of these features in it, both a beliefs and a learning channel. So that's it. Hopefully I'm relatively on time. So what is it that I want you to take away from this? Well, the bit that you're going to have to take on trust, but trust, it's very convincing, is that choice overload is a thing, that when you measure it properly, then we see choice overload and more choice overload than we would do using traditional methods. That you can get choice overload relatively easy, just coming out of an optimal response to the fact that there's uncertainty about the environment and that there's costs to search. So you can get it from optimal search behavior, but in order to do so, you need to assume something along the lines of learning or increasing search costs or static optimization. If we run an experiment that allows us to examine these different channels and compare them to classic explanations for choice overload, they show that the search channel does seem to be important, and probably more important than these classic models. And that it seems that both learning and increasing costs are important in driving this the choice overload. And where should we go from here? I think that if I've convinced you that models like this are a good explanation for what's driving choice overload, then we can start thinking about the welfare costs and benefits of different ways of defining choice, providing choice sets. So, imagine you're setting up your own health insurance exchange. We can use this to answer relatively basic questions like how many plans should I include and which plans should I include. But it also opens up the possibility to more exotic possibilities, like should I give information about the ranking of these different health plans or how many people like them? Should I try and guide people's search using sort of more exotic tools than just giving them a flat choice set which just has a number of alternatives they can choose from? And I think that would be a very exciting thing for someone to do. Okay, That's it. That's all I have. Thank you very much. Yes.
Oh, thank you. Great talk. I was wondering whether that low amount of choices that would support the classic model could be driven by the fact, by the experiment itself, right? The subjects were in an experiment where they were told, okay, so now you're going to search, so they search, right?
So your claim is that the reason that people are not searching, sorry, the reason that people are starting search is because they don't want to disappoint us.
Really, but this is pretty much the only thing they could do in the experiment, to search. So that's what they do.
That's right. I mean, okay. So I think there are. I think I've got two responses to that. One of which is that there clearly is some opportunity cost to search, because what they're not doing is completely searching all of these choice sets. So they are making a decision to stop searching at some point. So there is a cost to them to search. So I think there's still a version of the critique that is potentially valid, which is maybe there's some sort of non-linearity into these costs. That I feel somehow that I'm bad for if I really don't look at if I don't look at anything, then somehow I'm letting the experimenter down. And that is possible. I mean, I think even in the most so one thing is that, you know, prolific subjects, I think more than lab subjects, are sort of, you know, revenue maximizers, and so I think they're less bothered by stuff like that. We've actually run a bunch of these on Mechanical Turk, and we got very similar effects there. So I'm less concerned about that than I might be in the lab, where I think that you know, implicit motivation is quite strong. But I do agree that this is a possibility. I think all I would say is that what we've shown is that you can get at the very least, the most negative reading of our results is I can get you a lot of choice overload without any of those classic things. So you're right that maybe if we went out into, you know, if we went back to JAM and looked at people in then we would also get, you know, we get more of the classic stuff. But yeah, worst case scenario for our results is that you can get a lot of choice overload only using search stuff.
So, great talk. Let me ask a related question. What do these subjects know about the structure of these choices before they actually start uncovering them? And what I have in mind is, maybe if you knew that it's a sum of 5 numbers, then you wouldn't attempt it. But if you don't know that it's a sum of 5 numbers, then you just want to see what that option looks like, and you start searching.
I think they know a lot. So they have a couple of practice rounds, but probably more importantly, in the instructions, we didn't actually do this because we wanted them to know about the sums so much as we wanted to know about the distributions. But what they have to do in the instructions is quite laboriously. They're given like one of these 21 sets, and it says, first thing, these numbers are drawn from a distribution, and they have to press the draw button 21 times as the draws from the distribution come up. And then they say, and then these numbers will be converted into sums. And then they press a convert button, and then they're converted into sums. So I think, you know, you never can tell, but they've certainly had ample opportunity to understand the structure before they hit the actual practice, the actual paid rounds that we study.
Thanks. You did not mention the threshold function in the experimental part, which is whether you elicit them and what should they? Can you infer it from the data?
Okay, good. So you're right. For the search models, the threshold function is not the primitive. The primitive is the sort of the primitive is the beliefs and the costs, and that gives you the threshold function. What we haven't done, and I think, I suspect reviewers will ask us to do, and we should probably do before they do that, is one could consider doing a structural estimation of this. So we have observations of people continuing to search, and we have observations of people stopping search. So that should be enough. That's kind of enough to sort of like identify the threshold function. So then if we then roll that back and try and estimate, you could imagine a sort of, particularly seeing as we find both that it looks to us that both increasing costs and beliefs are important. One could imagine some sort of model that puts weight on both of these items both of these appear in the optimization problem, and then we could back out these relative weights. So no, we haven't done that. It's something I think we could do, and I think it's something that we should do, and will likely be forced to do.
Yeah, great talk, and thanks a lot. So I don't know if I missed it, but what's the role of the choice set N, and how much the knowledge about this set matters? I'm just thinking about on what you define as mistakes. Because so if they know that they're in a very large set or in a very short set, they may give up very quick because they know they may face a different a choice set that might be larger or smaller. And that might have an implication on the threshold function. So I don't know if this is considered.
Yeah, we hope that N is really important here, because at the end of the day, this is a study of choice overload. So it's a difference in how things work out differently when N is small and is large. In terms of the search models that we wrote down, N actually only appears in the model with learning, and this is just a result of the maths. With the model with learning, one of the important features that determines your threshold is, how much more have you got to go. So here, the size of the choice set. Let me give you the same history. So you've seen a 2 and a 1, but in one case you've got 40 things left to look at, and the other you've only got 3 things left to look at, then the threshold should be higher in the case where there's 40, because it's like, look, the learning is more valuable, because if this is a good choice set, I've got a very good chance of finding something good. So N should matter. When I talked about mistakes, I was talking about something much more crude. So because we don't have access to their costs here, we don't know what their individual costs here are, it's hard for us to say whether their threshold is a mistake or not. So when I was talking about mistakes, I was saying something a lot more crude, which is that the person had looked at 3 different alternatives. So the default was worth 5, and they'd uncovered a 7, but they'd still chosen the 5. So that's something that our model doesn't allow for, because in our model you pay your price and you uncover the utility. We could include it, but that's what I mean by a mistake, is that whatever your threshold function is, you should still choose the best of the things that you've not uncovered, and sometimes people don't do that. So we have to think about how to include that, possibly using a structural model. Okay. Sounds great. Okay, thank you.
Okay, so on behalf of the organizing committee, we want to thank Jan, Charles, for putting together a really nice pre-conference workshop, for Mark Dean to building the perfect bridge between the workshop and the coming Economic Science World Meeting. And to give you the official welcoming address, we have asked Hernando Soleta, the Dean of Economics at the department at Universidad de los Andes, to give you the welcoming address. Please, Nano.
Okay, thank you. Hello, I'm aware of the fact that I'm the only thing between you and the drinks, so I just want to welcome you. We are extremely happy to have the experimental community here, and please enjoy the conference, enjoy Los Andes, and enjoy the city. Thank you for being here. That's all.
So please go for your drinks and
I'll just put my slide on and then take a picture because I'm never going to be on this. I'm never going to have my
great. So let's ask. And do you want to put? Yes, great. So let me ask.
So, oh, you're doing a picture? Yeah, I'll take a picture.
But let me ask also